Okay. Okay. I do not know what is up with the little kitty stopped pawing there, and I don't know why. There we go. Okay. So we are starting our third unit, and it's likely going to be on psychophysical methods and how, of course, psychophysics means how do humans psychologically recognize physical signals, okay? And that is the main purpose of this third unit. But in parallel, interspersed in there, we're also going to be talking about a specific paper. We're all going to review the same paper. And so I want to get you set up for reviewing that paper. It will be, sorry, I thought I put it there, but I hadn't. It will be in the assignment section of Canvas, right after this class. And next week, today we're going to kind of prepare you for reading the paper. And then next Wednesday, we're going to review it together in class. Okay, so that we're all on the same page. And your job is to write that review. And we'll go over very specifically about what the review should look like, what parts should be there. And there'll be a really clear rubric and everything for you. And that's due November 20th, the Monday before Thanksgiving. We will not have class that Monday before Thanksgiving. You all are going to be working on your paper between 12:50 and 1:40 on that day. Okay. Okay, now you can work on it anytime, but it's due at midnight that Monday. Okay, so what we're going to do is we're going to set the stage for reviewing a research article. And today we're going to review the major sections that should be in a research article. We're going to describe what those sections should look like. And we're going to pay particular attention to the psychophysical methods used in our article and statistical methods more generally. Okay, how we think about statistical methods. Okay, so this is the article that we're going to review. And so you can see that here's my little pointer. Okay, so here's my little pointer. So let's kind of dissect this. Amplitude modulation. Does anyone remember what amplitude modulation means? It's also called temporal modulation. Anyway.
Like higher.
It's the change in amplitude over time. It doesn't change abruptly, it changes gradually. Usually with the sinusoidal, take all of this off, but sinusoidal shape pattern, okay? Okay, so okay, so the question is going to be, can you detect that amplitude modulation? How deep does it need to be for me to detect it? And the subjects in question are going to be children with a history of temporary conductive hearing loss. Why do you think they might have had temporary hearing loss?
Otitis media.
Otitis media, yes, especially otitis media with fluid in the middle of your cavity. And as we've said, you need good auditory experiences. The postnatal development of the auditory system is driven by auditory experience. And if you even have a temporary hearing loss, it's going to hinder that development. So here, not to give away the plot, but you'll see that it shows that this ability to recognize modulation, amplitude modulation in the signal is hindered for years after restoration of normal hearing. So that's what our article is on. Okay, so the sections that a research paper should have, an introduction, methods, results, and a discussion section. Today, okay, okay, so the three parts we're going to talk about are in the introduction, there should be a problem statement. The background should be rigorous and there should be clear hypotheses. In methods, and what we're going to talk about are participants, procedures, and stimuli. In the results section, we're going to talk about statistical analyses. Okay. Okay. So introduction, the problem statement. The problem statement should be, the topic needs to be important. It needs to be specific, a specific question being asked with the research, and this problem statement needs to give the reader a sense of what will be done. And I'm going to be asking you to write a problem statement about our article. Okay, so sometimes an article provides one. I think they all should. I always do, but you're going to have to put one together for our article and write it as part of your research review. Okay, here's an example of a problem statement. Cochlear implants have dramatically improved the likelihood that children born with severe to profound hearing loss will be able to develop spoken language skills within the range of typical children with normal hearing. Long sentence, but it's really clear, and that's good. Good news. We give children who are born very with severe hearing loss, we give them cochlear implants, and it means they'll be able to develop spoken language similar to that of their normal hearing peers. But, okay, here comes the problem. Nonetheless, significant deficits persist in some language functions that continue to inhibit children with hearing loss from reaching their full potential. Okay, so there's a problem there. Now it gets more specific. What specifically is the problem? In particular, children with hearing loss show challenges acquiring sensitivity to phonological structure. So specifically with phonological structure, not vocabulary, not syntax, but phonological structure. And the purpose of this study, so now it's telling us what the study's going to do. The purpose of this study was to examine the extent to which those challenges have their bases in speech production. Okay. Here are two more examples of problem statements that I've actually read recently. So you can see, so children can not think well when they come to school tired. We wanted to prove that was true. Well, first of all, no study, we never do research to prove something, right? We have to have a hypothesis, and it may go the way we think it's going to go, or it may not. Okay. So what do you think about this? Is this specific? Now, what does thinking mean? I mean, is that problem solving, memory, writing? What is that? And what does tired mean? Less than 6 hours of sleep per night, right? It's not very specific. Same thing with this one. Research suffers when women are not included as subjects. And this review of the literature looked at whether or not that is true. So again, just not specific at all. Okay. Rigorous background. The work, so the paper, you're going to be evaluating whether or not the paper you're reading describes rigorous research. But in order to design a research study, the research that it's based on, right? You can't just come up with an idea out of thin air. There has to be solid footing evidence. We're even suggesting that this might be the case. So is that rigorous research in and of itself? And the work cited, that rigorous research must be related to the study being described. Okay, testable hypotheses. Again, the hypothesis needs to be specific, and there must be a stated or null hypothesis. What other direction, what other answer might I guess for my question? And we never do research to prove an idea. Okay, so let's take a minute to read these. I'll let you read them. And then I want you to just, once you have, somebody raise your hand and tell me which one you think is more testable. Which one specifically tells us what's going to be done? Anyone?
One.
One. Okay. Who votes for one? Okay. Anyone vote for two? You'll have good taste. Why did you pick one?
Because it tells you what kind of tests they're gonna be and like, how they're gonna balance the results to make sure like the age for the cochlear implant matches up with the age that they started hearing the normal hearing kids.
Very good, very good. They have a control group there, right? My comparison is going to be that they're going to do more poorly than the control group, whereas in the second, it just says they're going to have trouble. What does that mean, having trouble? I have no metric, no reference, okay? Also, this idea that the role of age at first implant, when I say correlate, now I have age and I have how well they're doing, and I'm going to match the two. It's a continuous, in a continuous manner, but that makes sense. Whereas on the bottom one, they'll do better if they got their implants early rather than later. Well, what's early and what's later? 2 years, 5 years? I don't know. Okay, so, and number one is just more testable, and then the null hypothesis would be that these children with cochlear implants do exactly the same as the children with normal hearing. There's no difference. And it's not affected by the age that they got their implant. That they would be the null hypotheses, really. Okay, so let's look at methods, participants. Well, in general, are methods sufficiently rigorous as to yield results that are have a high likelihood of representing the situation in the real world? And could another investigator replicate the methods with the available information? Okay, we like replication studies. It's good to be able to, let me see if I can move this. This is just in the way down here. Okay, maybe you'll be less in the way up here somewhere. Okay, maybe not. Okay, so let's first talk about participants. Are the samples sufficiently large? And there are ways that people talk about that, but for me, it's just, are there a lot of subjects? Okay, and for me, rule of thumb is there have to be, if I'm comparing two groups, there have to at least be 20, but ideally at least 30. Okay, that's kind of rule of thumb for me. Are the samples well matched? Are they matched on age, on gender, socioeconomic status, and so forth? And this goes along with the one just before it. Are there confounding variables? Is there anything that could explain the results other than the factor I'm interested in, like the children with cochlear implants? Were the children with cochlear implants, did they have lower socioeconomic status? That can affect language. So if that group has lower socioeconomic status than this group, maybe any effect is not just because they're deaf and have cochlear implants. Okay, so you want to be keeping an eye on all of that. Procedures. Okay, so we are going to talk about psychophysical procedures. Again, psychophysics. Can anyone give us a definition of psychophysics from the first unit of this course? And what the course is all about. But you can kind of dissect it. The first part is psycho, as in psychological. The last part is physical, as in physical properties.
It's like a person's response to a signal or I know the words sensation and perception are involved with.
Okay, very good. Yeah, so how do we psychologically perceive and process physical properties in the real world? We're interested in acoustic signals, but if you're a vision scientist, it would be vision, for example. Okay, so usually in psychophysical experiments, and remember, Fechner is the person who first developed, who got the idea, oh my gosh, I think I can measure how people respond to physical properties. And all of you, if you're going to be an audiologist or an SLP, psychophysical studies is what you're going to be doing every day of your career. How does your patient or your client respond to the language stimulus or the acoustic stimuli in the world? Okay, so these methods, on Friday, you'll have an at-home lecture on psychophysical methods, and that is the basis of everything that you're going to be doing in your career. Okay, and it's all based on the normal ogive. And to get a normal ogive, an ogive is a normal cumulative curve that looks like this, and it's based on the method of constant stimuli. So in the method of constant stimuli, I have some physical property represented here in the x-axis. It can be anything. Amplitude of an acoustic stimulus, and it goes from low to high, and I play it in each stimulus. The stimuli vary in discrete steps, and I play each stimulus numerous times in random order, and when I disentangle all the stimuli and look at the results, I see that as the stimulus gets higher in amplitude, my listener is more likely to recognize it. So I get something like that. Yeah. Okay, makes sense? Okay, so that is the normal cumulative curve. But what is a threshold? Often I just want to know about one point, and I define something called a threshold. Often it's the 50% point. That's what people usually think of as the threshold, where half the time I can hear it and half the time I can't. So where is that threshold? At what value on the x-axis? Okay, so here are some stimuli that I'm going to use to illustrate how you get an ogive, a normal cumulative curve. And so these stimuli they're speech stimuli. Anyone want to hazard a guess as to what they are? Can anyone tell us anything about them? Have any ideas about them? You think they're whole sentences or isolated vowels or syllable or? No? Okay. Okay, so these are waveforms up here. What do we call this part down here, this graph?
Spectrogram.
A spectrogram, right. So we have time here and frequency here, and the amplitude of each frequency band is represented by the darkness of the tracings. And so what do we call these dark bands here? Formants, thank you very much. So here's the first formant, the second formant. This first formant is pretty high. If it's high, do you remember when a formant is high versus when it's low? What does that tell me about what the jaw is doing? Let's give somebody else a chance. Okay, when the jaw is closed. Okay, you know what, let's draw I'm gonna draw on the board here a vowel quadrilateral. Here's F1, okay? Here, I'm gonna say, even though it sounds counterproductive, I'm gonna put it here F1 is high, here it's low. Okay, so what does this tell me about what the jaw is doing? Do you remember when the jaw is raised as an E or U, F1 is low, right? But as I lower the jaw, remember the tongue retracts back, and now there's a perturbation at that node just above the larynx, and a perturbation pushes F1 up. So when the jaw is low, F1 is high. So here, the jaw is low, and you can see F1 is rising here. So here, the jaw was closed. F1's low, closed jaw, it's opening, and now I have an open jaw. Okay, so this vowel is ah. And so this says 0 milliseconds. This is 40 milliseconds. Do you remember voice onset time? So these are two stimuli that differ in voice onset time, from 0 milliseconds voice onset time to 40 milliseconds. Okay. Okay. So what else do we want to know? So this is, I'll just tell you that because F2 and F3 are both falling, that is an indication that this is an alveolar constriction. So let's listen to what these are. The first one is over here that has a voice onset time of, what do you think it's going to be? The one with 0 milliseconds. And what does an alveolar constriction mean? Can anyone tell me one syllable that begins with an alveolar constriction? Constriction of the alveolar ridge. Okay, well, let's listen to this one. It has an alveolar constriction and a voice onset time of 0 milliseconds. What did you hear? No, doesn't make sense to anyone? What was it? Does it sound like da? Okay, good. That's what it's supposed to sound like. Yeah, so it's da, right? Made at the alveolar ridge, voice onset time. It's voiced, categorically it's voiced. And what do you think the next one's going to be? If the first is da, and this one is the counterpart. Ta, thank you, yes. Okay. Okay, so we have da and ta based on the voice onset time. And voice onset time is the time between the release of that closure and the onset of glottal pulsing. And you can see that also goes along here where it's voice onset time is longer. We have aspiration noise here, and there's no F1 here. Okay, so if I played every stimulus, just like we heard, with voice onset time between 0 and 40 milliseconds, and I played everyone multiple times, and then looked at whether or not my subject told me I heard da or ta, this is what I would get. An ogive like this, okay? And I would use method of constant stimuli for this because I want to know what that ogive looks like. Is it steep or is it more shallow? Because some listeners with speech perception problems, they don't really pay attention to voice onset time. So then I'd have a very shallow function. Listeners of different languages use different acoustic properties differently. Okay, so if I'm a speaker of a different language, I might not pay attention to this particular cue to voice onset time. And in that case, I'm going to have a shallower function. So for speech, for this kind of experiment, I want my whole ogive. And the boundary, I put a boundary here at the 50% point. That's called the phoneme boundary or threshold. So I go from hearing mostly da to hearing mostly ta at that point. But sometimes I don't want to see, I don't care about the whole ogive, right? I only care about that threshold. So if I'm presenting lots of stimuli out here or lots of stimuli down here, it's just a waste of my time. It's a waste of my time. It's a waste of subject time. You know, if I'm working with children, they get bored. So I just want to know, how can I zero in on stimuli around my boundary and focus my time there? Okay, and to help us with that, along came our friend who you can't see here. I'll move this out of the way, but it's Harry Levitt, okay? Harry Levitt came up with the method of transformed up-down adaptive procedures. So I quickly figure out about where my boundary is, and then I just spend my time presenting stimuli there and don't worry about all those stimuli far from my boundary, okay? And sometimes I don't care about the 50% boundary. sometimes in this case, this is at about 70%. Okay, if it's at the 50% boundary and I'm working around there, half the time my subject's not going to hear it. Right? And half the time they will. Well, with children don't like it when they're not hearing what they're supposed to. So I'm going to lose their attention. So I work at the 70% boundary, where 2 out of 3 times pretty much the child is hearing what they're supposed to be hearing. So that's a lot more fun and I can keep the kids' attention. But to do that, I need different rules. And Harry gave us these rules, these transformed rules. If the subject gets 2 correct, I decrease whatever it is. I decrease the amplitude or the difference between the stimuli or whatever. And then if they get it wrong, now I make that difference or that amplitude greater. And that zeroes in on a boundary. And we'll be seeing how that works here in a second. Okay. So that's transformed up-down methods. The paper you're going to read uses them. Everybody uses them in psychophysical research. So the stimuli that we're interested in are band-limited noises modulated with sinusoidal envelopes. And we call that temporal modulation or amplitude modulation. And this is what the stimuli look like. Okay, so here's unmodulated noise. And here's modulated noise. Okay, it's modulated because I put this sinusoidal shape on them. So why noise? Why not just use a sinusoid, a single frequency, and amplitude modulate that? Remember, we talked about doing that in the first part of this course. You remember what the spectrum, remember you can take a sinusoid and I can shape the amplitude with a slower modulating envelope so that I get something that maybe it's high amplitude here and then a slower amplitude and then it's higher amplitude, right? Remember that? Do you remember what the spectrum looked like for that? Right, so spectrums are a frequency here and amplitude here. Remember that whatever the frequency of my main sinusoid was, I had the center frequency. Then remember I had 2 side frequencies. One was the frequency of that minus the frequency of modulation, and the other was the center frequency plus the frequency of modulation. Well, if I used a sinusoid, right, that would always be varied. And so I'd have a secondary cue to the fact that there's modulation there, right? So, because these signals on the side, if these are just plain sinusoids with no amplitude modulation, it would only be that. Whereas the one with modulation would have these little sidebars. So that would be my other cue. Okay, so but with noise, it's just all kind of mixed in there. The spectrum just always kind of looks like that because that's what noise looks like. Okay, and it's always changing. So you don't get those little sidebars. Okay, and the modulation is sinusoidal, as we said. And now we're going to, as our metric of how deep is that modulation, we're going to use this formula. And this formula should look like an old friend of yours, 20 log something, right? In sound pressure level, we use 20 log R, where the denominator is 20 micropascals usually, and the numerator is whatever the pressure is of the signal. But remember, I always said, but that doesn't have to be the case. You can compute dB with any reference you want. Well, in this case, it's the amplitude of that noise. What's the amplitude of this noise? And the numerator is the depth of that modulation. Okay, so I'm going to come back to the board, erase all of this and see. I want to make sure that you understand our metric for designating depth of modulation, because you can see there, like the signal down here at the bottom, this says that modulation depth is 0.5. So you can see it's not as steep. It's only half as steep as the amplitude of the noise, right? So that's the whole point of our paper. How deep does the modulation have to be for these kids with histories of otitis media to recognize that it's there? As children grow up, they're born and their auditory systems develop. And one thing that develops is that they come to have better amplitude modulation detection. So the signal does not need to be as deep for them to recognize it as they get older. If you have auditory problems, like you had a history of otitis media, that development is hindered. So you're still going to need it to be deeper. What that means is that your perception of speech is not going to be as good, right? Because sometimes in speech, there are little, you can look at a waveform of speech, there are just little changes in amplitude that tell me something about the signal. In fact, if I come all the way back here, let's go back for a second to our, see, you can see right here, oh, another cue to this, this had a long voice onset time. Look, I've got a dip in amplitude, whereas here I don't have that dip. So the amplitude of the signal and these changes in amplitude tell me about the signal that I'm listening to, okay? So now, so that's the question that we're interested in. And, well, let's move on. I'll come back to how we specify that in a minute, I think. Okay, so we're going to use an adaptive procedure, 3-interval forced choice. That means the subject is going to be presented with 3 sounds. 2 of them have no modulation. 1 does. It doesn't have to be in the middle. It can be on one side. And the subject has to say which one had the modulation. And I'm going to vary it if they get it, if they respond correctly 2 times. I'm going to make that modulation not so deep. If they get it wrong, I'm going to make it deeper. And I'm going to find the threshold and work around the threshold. And I'm going to have 12 of those changes. And I'm going to do that 2 times. And as you'll see, I'll compute the threshold as the mean of the last 8 reversals. Okay, so this is what it looks like. In my lab, a child sits in front of a computer monitor and sees 3 cute little kitty cats. And, you know, I love cats. Mm-hmm. So we say, one of these cats is really a dog. And you'll know because it makes a different sound. And so you have to tell me which cat is really a dog. And so they hear, and they say, oh, the cat in the middle, number 2. And it's like, ah, you're right. That was really a dog hiding under there. Okay, so that's how we play the game. And here, over here, this is what the adaptive track looks like. I got it. This is the deepest it can be. Okay, now let's talk about this. So those numbers on the left there, that's modulation depth in dB. And we said it equals 20 log M. And we said M is the depth of the modulation over the amplitude of the signal, right? Is everyone with me? Yeah, okay. Okay, very good. So if the depth equals the amplitude, as it says there, see at the top there it says mod depth equals 1. Okay, so M equals 1. What's the log of 1? Did someone say 0? Yes, very good. So the log of 1 is 0. 20 times 0 is what? 0. So 0 dB means it's as deep as it can be. So now M is only going to ever be a fraction. Remember, if you have a fraction here, you're going to have negative numbers there. So this goes up to minus 20, right? So minus 20 is 1/10, right? As deep. So that's what that is. And you'll recall it this, and like in the next one here. So that's 0.5. So here M is 0.5. Well, you know that if I double my amplitude, it's an increase of what? 6. If I have it, it's a decrease of what? 6. So -6 would be half, -20 would be 1/10. Okay, so thresholds are getting better, and I would expect children without histories of otitis media to be down here someplace, and the children with otitis media to have poor thresholds. Okay, everyone clear on how we're going to measure depth of detection? Okay, now frequency of detection. Sometimes I want to know, you know, I can vary the frequency. Here it says 8 hertz up there, right? At the top. Well, 8 hertz means I get 8 of these spectral prominences every second. Well, here I have half a second, so I can expect 4, half of 8. Sometimes I might want to look at a higher modulation rate. This has 16. But sometimes I might want to look at something lower. So this is a modulation rate of 4. So I only have 2 of these prominences in half a second. Okay, that's a very low modulation rate. But now I can go up really high. In speech terms, these low rates of modulation, that's like what you're doing with the jaw, opening and closing and changing amplitude that way. This really fast one, this is like what you do with the larynx, with the opening and closing of the larynx. So depending on the modulation rate, I'm asking if you can recognize, how well you can recognize the envelope of speech versus fundamental frequency. Okay. Okay. And I can measure these different ones. And if I plot them out, which we've done in my lab, now this is a low rate of modulation. This was 4. This was 16. We saw those. This was 64, and then they get even higher. So now again, 0 down here is as steep as it goes. So this would be, if you had a amplitude modulation detection threshold of 0, you've got really bad abilities to recognize that kind of structure. -20, you're pretty good. Okay, so we did this. If I can move you back out of the way here, thing. Oh, come on. Oh, you know. Okay, so now we did this. We had adults, we had older children, 8 to 10-year-olds with no otitis media history, 5 to 7-year-olds with no otitis media history. And immediately you can see there's a developmental effect. This ability to recognize this isn't developed in 5 to 7-year-olds, and you're going to be working with kindergartners. Okay, they don't recognize sound the same way that you do. You're going to have to remember that. And then the ones who had histories of otitis media, look, they're even poor. And look at the difference between them and the adults or the older kids. That's a big difference, guys. Okay, so those little kiddies with histories of otitis media, they don't recognize amplitude modulation very well in my study. You'll see what happens in the study you're going to read. Okay. Now, in the study that you're going to read, they kept their modulation rates right here in this nice, easy to measure area. Okay, this middle area, not too low, not too high. Okay, you'll read all about it. And we call this a transfer function. Anytime you measure the same thing across conditions like this and then plot it, it's called a transfer function. Okay. So that describes for you, and I hope this is a bit of a cliffhanger, the methods and the stimuli that are used in the study you're about to read. And I want you to read it this week. Now, how do we have till 1:40? Okay, perfect. How do statistics? Okay, iClicker question. Have you taken a statistics course before? Yes or no? I'm going to take a poll here. No. Okay, I don't, oh, that might be everybody. Has anyone not responded? Oh, that was fast. Okay, let's see. Okay, everyone's taking the statistics course. Very good. Next question. What do you think the next one's going to be? How confident are you, in spite of having taken that course or because of taking it, that you could read a research article and understand the statistics? Okay, you're very confident. Yes, you're confident. Or no, you're not very confident. Okay. Anyone not respond? Okay. Quick answering here. Okay. Oh, did you all answer? That is utterly amazing. That is exactly the distribution of the first class. It's like, wait, is this from the first class? Except the numbers are different. But the same distribution of 57 and 43. Wow, okay. Okay. So half of you kind of are confident you can, half can't. We're going to go over statistics. You know, I want you all to be able to think conceptually. Okay, sometimes I fear that you've been given details, like in statistics. This is how you compute an F ratio, but you don't understand from the 30,000 foot level, what does that mean? What do these results mean? So I want you to be able to understand how to use that knowledge to interpret the results in a research paper. And, I'm sure a lot of you can, half of you can, 16 out of 28. But let's just go over it a little bit more. Okay, so when I am doing any kind of statistic, I have some variable along my x-axis here. So it could be how tall are men in Wisconsin? Short and tall, and I'm going to measure them all. How much do salmon weigh swimming upriver in Alaska? They can be light and they can be heavy. Whether children's scores on the language test, low or high, how fast do tortoises move? Whatever it is. So I'm going to go out and I'm going to start making my measurements, and I'm going to collect a whole bunch, and this would be lining them up in vertical measure. At any one measure, I get this many, and another measure, I get this many, and I end up with something that looks like this. Does that look familiar? What do we call it? A bell curve, yes. And it's got a mean and standard deviations. It's called the bell curve, right? And it is symmetrical about the mean. And in fact, when it is completely symmetrical, one way I know it's symmetrical is because the mean, the arithmetic mean, equals the median, the point where half of the subjects are below and half are above. Now, in terms of standard deviations, plus or minus one standard deviation from the mean, if it is symmetrical, has 34% of the subjects. Okay, this is area under the curve that you probably had in your statistics course. Yes, you had to compute area under the curve. Okay, and two standard deviations, that next between 1 and 2 standard deviations in either direction is another 14%. And then the last is 2%. And again, these are the percentiles. These are standard deviations. So this is what the normal curve looks like. And again, that 34% between -1 and the mean or +1 in the mean, it's always 34%, whether variance is tight like that or very broad. Okay, it's always the same. So that's the population distribution. That's of all those salmon swimming around up in Alaska. But maybe I want to use this for a study. I want to have two samples and compare them. So I go and collect weight on one group of salmon, and this is what I get. Okay, very good. Now, what I want to know if the salmon this year weigh as much as the salmon last year. So I have my data from, say this is the data from last year. I collect more data, and this is what I get. Ooh, the means are a little different. Do I conclude that salmon this year are not as big? And it's a little different. But there's variability, right? There's all kinds of variability. There are salmon in my first group that have this weight, and there's salmon in my second group that have this weight. So how do I know if that difference is statistically meaningful? Well, that's when you do a statistical test, which is always comparing those means. Okay, you have to compare them. And I'm going to tell you the critical question is always, is the difference in those group means greater than what I would expect based on the variability within any one group? Okay, that is the critical question. So to do that, I'm going to have to come up with some kind of ratio, and we love ratios. What's the difference between those means, and what's the variability in the groups? And if that's the same, if that ratio is pretty close to 1, I'm going to conclude, there's no difference, right? Both groups basically come from the same population. Okay, so again, and I think my little picture is going to be in the way here. Let's put you down. The two rules for comparing samples is the distributions have to represent the normal curve, and the distributions have to be fairly similar, not exactly perfect. But you can't have one distribution like this and one distribution like that. They have to be pretty similar in shape. So we always check that first. If they're not similar in shape, there are workarounds, but it's always nicer to be able to do this kind of comparison. Okay, so here you can see that clearly the difference in these means are greater than what I would expect based on how variable the groups are themselves. Okay, and our yardstick is 1 standard deviation, and how we gauge it's different is the difference between group means would be greater than what we'd expect based on within groups. So again, this isn't exactly the formula, but it's pretty close. The difference in the means over the pooled, that means estimate, averaging standard deviation across my two groups. Okay, so just to kind of, last point here is, in your paper, so a t-value is used with two groups, and it's the ratio of the difference between the groups over the variability within separate groups. An F ratio is usually reserved for studies with multiple groups, and that is the ratio of variability among the group means over variability within the separate groups. And just to let you know, for some reason, in all of the effects that are studied in the paper you're going to read, there are always 2 of everything. 2 groups, children with otitis media, children without, 2 levels of modulation frequency. But sometimes the authors computed an F ratio, and sometimes they computed a T statistic. So that can make it seem hard to compare between them, but you just have to remember that F equals T squared. So when you're reading, either square your T or take the square root of the F. Okay. And a p-value is the probability that you would get the ratio you got, or the difference between the means you got, strictly by chance. Because maybe the 2 groups are really different, but you just sampled funny. Okay, so you fail to find that there's a difference. And usually we put that boundary at 5 out of 100. So if there's less than a 5% chance that I would have gotten this result by chance, I say, ooh, there really is a difference. I'm going to conclude there really is a difference. Okay. Okay. So that is, and we call it an alpha. You may have seen this alpha equals 0.05, so that's a 5% chance in 100. Okay. So, in general, for results, you want to ask, do the results address the hypotheses? How solid do the results appear? And for the discussion, does the discussion address the problem presented in the introduction? And does the discussion explain the real-world significance of the results? So with that, all that in mind, for the rest of this week, you need to read chapters 28 and 29. Watch the lecture on Friday, and on Monday, you'll have another at-home lecture. Next Wednesday, we're going to meet in this very room. And please read your research articles for that. Okay. Okay.